Hello, my name is Jessica Kernigan, and I'm going to be presenting on my project from this summer, Nickel-Mediated Decarbonylation of Phthalimides. First, for some quick background, transition metal catalyzed decarbonylation reactions, as shown here, are very important reactions in chemistry because they allow for the creation of new carbon-carbon single bonds, which is very important in many different syntheses. However, the metals used in these reactions are generally quite expensive. So this summer, I explored the use of nickel as a cheaper alternative. There is some literature examples of this. For instance, the Johnson group achieved stoichiometric decarbonylation of phthalimides, as shown here, using one equivalent of nickel cod. They also attempted a catalytic version of the reaction, but got very low yields and determined it didn't work. They proposed a catalytic mechanism, which included this nickel metallocycle intermediate. They believed that the catalytic cycle was not achieved because of the strong bond between nickel zero and carbon monoxide. A different group did achieve catalytic decarbonylation of biheteroaryl ketones using nickel, 10 mole%. They also proposed this nickel metallocycle intermediate. Finally, the Hoover group was able to isolate a nickel metallocycle with a labile CO using a quinoline group. This led to the hypothesis that the addition of a coordinating group to N-phthalimide will assist with releasing CO and result in catalytic activity. In order to test this, I did the reaction with both the phenyl, which according to our hypothesis should not result in catalytic activity, and the quinoline, which should result in catalytic activity. In order to do this, I synthesized N-substituted phthalimides and ran the stoichiometric and catalytic decarbonylative reactions to give us these orthosubstituted benzoamides. A different part of my project was the synthesis of nickel metallocycles using both the phenyl and quinoline aryl groups. The first part of my project this summer was synthesis of starting materials, specifically N8 quinoline phthalimide and N-phenylphthalimide. These phthalimides were then used for decarbonylative coupling reactions. I want to first talk about the phenyl version. I successfully did the stoichiometric and catalytic decarbonylative coupling using N-phenylphthalimide. The stoichiometric version of the reaction gave a 38% yield, while the catalytic gave only a 4% yield. This stacked plot with the stoichiometric version on top and the catalytic on the bottom shows that the product peaks present in the stoichiometric all but disappear in the catalytic, which confirms our yield. Next, I did the stoichiometric and catalytic decarbonylative coupling of the N8 quinoline phthalimide. The stoichiometric version of this reaction gave a 20% yield, while the catalytic gave a 12% yield. This led to the conclusion that using N8 quinoline phthalimide compared to N-phenylphthalimide resulted in a higher catalytic yield. The next part of my project was the synthesis of nickel metallocycles. I attempted the synthesis of a nickel acyl complex using N-phenyl, which is the intermediate in order to get a nickel metallocycle. However, I only got back starting material and it resulted in nickel plating. I was, however, successful in the synthesis of a quinoline nickel metallocycle. This was done in two parts. First, the synthesis of the nickel acyl complex with the quinoline group. This is IR, shows the two carbonyl peaks. And then that nickel acyl complex was used in the synthesis of the nickel metallocycle. You can see the shifted carbonyl peak attached directly to the nickel is now at 266, which indicates that we did successfully make the nickel metallocycle. Conclusions: I performed successfully the stoichiometric and catalytic nickel decarbonylative cross-coupling of both the N-phenyl and N-quinoline phthalimides. In both cases, the stoichiometric reactions provided higher yields than the catalytic versions of the reactions. However, the catalytic decarbonylative cross-coupling was far more effective with the N-quinylphthalimide, giving a 12% yield than the N-phenylphthalimide, which only gave a 4% yield. For future work would be the synthesis of new N-substituted phthalimides and testing their reactivity using the same reaction conditions as done previously. Next will also be to test the reactivity of the nickel metallocycle synthesized during the summer and see if we get the same orthosubstituted benzoamine product. This could help confirm our proposed mechanism for this reaction. Thank you.